5,000 gallons of diesel. That's what sits in the tank of a GEES 44 AC freight locomotive before it departs on a single scheduled run. The job ahead will burn only a fraction. The rest rides along, untouched. Now scale that to every freight locomotive dispatched across North America in a given day, millions of gallons in constant motion that no one plans to burn. Everything you know about fuel economy says this is waste. But those rules come from a world where every extra pound is the enemy. On steel rails, the physics tell a different story, and that rewrites everything you assume about what all that fuel is actually for. A single GEES 44 AC road locomotive sits at the terminal, its massive frame resting on 6 steel axles. Beneath the cab lies a steel fuel tank holding 5,000 gallons of diesel. The assignment ahead is a typical freight run, hauling a 3,000-ton load across a 500-mile route. Because railroads keep internal logs confidential, exact public records of departure and arrival fuel gauge readings for this run do not exist. Instead, engineering models reconstruct the mathematics of this trip. At a standard fuel consumption rate of 535 ton-miles per gallon, this 500-mile run will consume roughly 2,800 gallons of diesel. When the locomotive rolls into its destination terminal, the physical fuel gauge will show about 2,200 gallons remaining in the tank. This is not a theoretical mathematical discrepancy. It is a physical reality. Thousands of pounds of liquid fuel riding untouched in the bottom of the tank, carried across hundreds of miles of track only to be left unburned at the end of the trip. The puzzle is why a railroad, operating on razor-thin margins where every penny is tracked, would routinely pay to transport 2,200 gallons of diesel it has no immediate intention of using. Scaling this single run across the entire rail network expands the puzzle. Industry estimates suggest roughly 13,000 active road locomotives operate daily. Applying a modeled average surplus of 4,300 gallons across that entire fleet produces an estimated total of 56 million gallons of diesel, riding untouched in fuel tanks at any given moment. At 7.1 pounds per gallon, this equates to roughly 180,000 tons of fuel mass. Thousands of tons of fuel travel through the network without being consumed. Because no public registry measures exact national inventories, this order of magnitude estimate remains sensitive to changes in run lengths, throttle settings, idle times, and fleet definitions. The mathematical model exposes a physical reserve hauled across the continent. It leaves open the central question of whether this national surplus is an expensive logistical failure, or if it serves a deliberate operational function. The underlying question is why diesel locomotives are designed and filled for capacity far beyond a single scheduled freight trip. Here, unused fuel does not mean unwanted fuel. It refers strictly to the diesel remaining in the tank at the end of an assignment, carried but not consumed. Resolving this puzzle requires examining 3 distinct areas: physics, operating constraints, and network economics. Other transport modes, such as cargo ships, heavy trucks, and aircraft, apply entirely different rules to their fuel supplies. In those industries, carrying any onboard weight that does not directly contribute to the immediate trip is treated as an operating penalty. This familiar assumption, inherited largely from aviation, suggests that hauling tons of unburned diesel across the rails must incur a heavy financial cost. In commercial aviation, weight is the constant enemy. Every extra pound loaded onto an aircraft demands more lift, which in turn generates more aerodynamic drag. To overcome this drag, the engines must burn more fuel, creating a compounding cycle where carrying fuel actually costs fuel. Flight planners must calculate this penalty with extreme precision. Loading an extra 5 tons of reserve fuel onto a typical 70-ton passenger jet increases its takeoff weight by about 7%. Because of the physics of flight, this additional mass can reduce the aircraft's range or increase its trip fuel consumption by nearly the same percentage. Airlines refer to this penalty as the cost of carrying fuel. If a plane lands with thousands of gallons of excess fuel, it means the airline paid a premium to transport that weight across the sky, dragging down the flight's overall efficiency. This basic equation creates a powerful incentive to keep fuel tanks as empty as safety regulations allow. Every gallon of unnecessary weight left behind directly improves the flight's profitability. This logic is so deeply ingrained in transport economics that we naturally apply it to everything that moves. But a steel rail operates on a different set of rules than the open sky, raising the question of whether a locomotive actually pays the same penalty. An airplane must actively fight gravity to stay aloft, continuously burning fuel, just to keep its own fuel supply in the air. A train operates on an entirely different physical foundation. Instead of generating aerodynamic lift, a locomotive relies on the earth to bear its weight directly, transferred through the rigid contact of steel wheels resting on steel rails. This physical support fundamentally changes the energy required to carry a load. To understand why, we look at rolling resistance. This is the physical force required to keep supported wheels moving forward, overcoming the microscopic deformation of the steel wheels and rails as they roll against each other. For trains, this coefficient of rolling resistance is remarkably low, typically ranging between 0.001 and 0.002. To see how this plays out in practice, consider a single locomotive illustrative example. When a standard locomotive is topped off with an extra 5,000 gallons of diesel, it adds roughly 35,500 pounds of weight to the track. To calculate the extra rolling resistance this weight generates, we can multiply that 35,500 pounds by a typical rolling resistance coefficient of 0.0015. The math yields an astonishingly small number, just about 53 pounds of additional resistance. 53 pounds of extra drag is a minor force, easily overcome by an engine designed to pull millions of pounds. Compared to the massive lift burden of aviation, transporting this extra weight across the rails is exceptionally cheap. However, it is not literally free. The locomotive still must burn a small, measurable amount of energy to overcome those 53 pounds of drag over hundreds of miles. There is a clear distinction between a carrying penalty that is exceptionally small and an operation that is entirely cost-free. Hauling thousands of pounds of unused fuel still requires energy, but the physical reality of steel on steel minimizes that penalty to a fraction of what any other transport mode experiences. A massive freight locomotive can output over 4,000 horsepower, yet that immense power is useless if the wheels simply spin in place. When a heavy train attempts to start from a dead stop, the limits of steel-on-steel contact become immediately apparent. If the rotational force applied to the driving wheels exceeds the physical friction between the wheel and the rail, the wheels lose grip. This is wheel slip, a mechanical failure of adhesion that prevents the train from moving. To overcome this, railroads rely on a fundamental distinction between engine horsepower and starting tractive effort. Horsepower determines how fast a train can pull a load once it is already moving, but tractive effort is the actual pulling force the locomotive exerts to get the train started. This tractive effort is calculated by multiplying the rail's adhesion coefficient by the locomotive's adhesive weight, the downward gravitational force pressing on the powered wheels. On clean, dry rails, that coefficient typically ranges between 0.25 and 0.35, meaning the maximum starting pull is only about 30% of the weight resting on the axles. Wet or contaminated rails drop this number even lower, triggering immediate wheel slip. This is where the fuel tank acts as physical ballast rather than passive cargo. Positioned low in the frame, a full 5,000-gallon fuel tank concentrates roughly 35,000 pounds of mass directly over the powered trucks. This weight increases the downward force on the axles, raising the tractive effort the locomotive can apply, before the wheels spin. Still, this ballast effect has strict limits. Railroads must balance maximum locomotive weight against axle loading limits to prevent track damage, and as the engine burns through fuel during a run, this adhesive weight steadily declines. Unused fuel is not dead weight. It performs an active mechanical function. But if this weight is managed so precisely, why carry so much excess endurance in the first place? During the steam era of the 19th and early 20th centuries, locomotives were bound to a dense, rigid network of trackside infrastructure. Steam engines required constant attention, stopping every 50 to 100 miles to replenish massive amounts of water and coal or oil. This frequent servicing shaped the very geography of early rail routes, anchoring towns and maintenance facilities at short, regular intervals. The rapid transition to diesel-electric power in the mid-20th century dismantled this operational model. Diesel units could travel hundreds of miles without stopping for servicing, allowing railroads to tear down labor-intensive coaling towers and water treatment plants. However, this transition did not eliminate the geographic constraints of fueling. It merely concentrated them. Unlike freight trucks that can pull into thousands of commercial roadside stations, a locomotive relies on a highly specialized, sparse fueling network. Today, diesel depots are located almost exclusively at major classification yards, main engine terminals, and select high-volume route locations. On the Pacific Northwest Corridor, for example, viable refueling sites are spaced about 200 miles apart, while remote western routes can stretch over 300 miles between functional depots. Because of this sparse layout, a locomotive is rarely fueled solely to complete its immediate scheduled run. Instead, dispatchers must look beyond the scheduled mileage of a single trip to the distance to the next capable fueling facility. A locomotive must carry enough diesel to bridge these vast gaps, allowing it to safely venture into unpredictable network territory where no fuel is available. A larger starting fuel level provides the operational security to navigate these geographic constraints. But this spatial challenge represents only one dimension of railroad logistics. The true measure of a locomotive's fuel requirement is not just the physical distance it must cover across the map, but the sheer amount of time it spends along the way. A locomotive's assignment is rarely an uninterrupted run from origin to destination. For hours, and sometimes days, the controlling variable of a trip is not physical mileage, but the passage of time. Freight trains routinely spend hours stationary, waiting in classification yards, sitting on passing sidings to let higher priority traffic pass, or idling in terminal queues during crew changes. During these extended pauses, the engine continues to burn diesel, consuming fuel without adding a single mile to the odometer. For a single modern road locomotive, the idle fuel consumption rate ranges between 3 and 6 gallons of diesel per hour. Over a 12-hour stationary wait, a single unit will burn through approximately 36 to 72 gallons of fuel, simply keeping its auxiliary systems active. Shutting the engine down to conserve this fuel is often an operational gamble. On older locomotives, restarting a massive 16-cylinder engine can be highly unreliable. If the engine block cools down too much, the battery may fail to turn the starter, or the fuel system may lose pressure. Cold weather complicates the decision further, because these massive diesel engines use pure water rather than glycol-based antifreeze in their cooling systems to optimize heat transfer efficiency. A shutdown in freezing conditions risks catastrophic engine block cracking. The risk of blocking a main line with a dead locomotive far outweighs the cost of the diesel burned while idling. Modern locomotives employ automatic engine start-stop controls and electronic monitoring. These systems track battery charge, cabin temperature, air brake pressure, and engine block temperature, automatically shutting down the prime mover when safe and restarting it when vital parameters drop. While these retrofits can save roughly 15,000 gallons of fuel per locomotive annually, they reduce, rather than eliminate, stationary consumption. The unpredictable nature of rail networks means engineers often face delays of uncertain duration. If a train is cleared to move at any moment, the thermal stress of repeatedly cycling a massive diesel engine makes shutting down impractical, leaving the engine to idle and steadily draw down the onboard reserve. A freight train's journey is defined by its manifest, but the locomotive hauling it follows a completely separate itinerary. When a train rolls into a major classification yard, its cargo is sorted and sent to various destinations. The locomotives, however, do not remain with their original load. Instead, they enter a system known as a power pool, where railroads treat these multi-million-dollar units as highly mobile, shared assets. Upon arrival at a terminal, crew members uncouple the locomotives and move them to a service track for a rapid inspection. A unit that just finished a flat, low-resistance run along a river basin might be immediately reassigned to haul a heavy coal drag up a grueling mountain grade, or sent on a high-speed intermodal run in the opposite direction. Because of this constant reshuffling, a locomotive's next destination is often entirely unknown at the time it is fueled at its origin point. The original train's calculated fuel requirement becomes completely irrelevant the moment the locomotive is detached. This assignment uncertainty makes operating with a low fuel level a severe logistical liability. While some industry accounts claim railroads enforce a strict 80% departure target, actual fuel tickets and dispatching targets are highly proprietary and kept confidential by Class 1 carriers. What is clear is that a locomotive arriving with thousands of gallons of diesel still in its tank provides the dispatcher with immediate flexibility. It can be reassigned to any departing train without wasting hours waiting at a crowded refueling platform. Keeping these tanks heavily loaded serves as a buffer against terminal delays and sudden schedule changes. Yet this logistical cushion also unlocks another major advantage. The decision of where to buy these thousands of gallons of diesel is not just about keeping the engines running. It is a calculated financial strategy that exploits the geographic price differences of fuel across the rail network. Diesel prices are not uniform across a national rail network. They vary by state taxes, local environmental regulations, regional refining capacity, and specific supply contracts. By August 2026, Energy Information Administration data showed average retail diesel on the West Coast reached $6.13 per gallon, with California prices climbing past $6.70. Meanwhile, Gulf Coast prices sat at $5.14 per gallon, a difference of nearly $1 for every gallon pumped. This price geography creates an opportunity for fuel tankering. In railroad operations, tankering means buying extra diesel in a cheaper territory and carrying it into a more expensive one, bypassing local refueling stops where fuel costs more. To calculate whether this strategy works, railroads must separate gross savings from net savings. Gross savings are simple: the price difference multiplied by the extra volume purchased. If a locomotive takes on an additional 2,000 gallons of cheap Gulf Coast diesel, instead of buying it on the West Coast, the gross savings approach $2,000. But carrying that extra fuel is not free. Those 2,000 gallons weigh roughly 14,000 pounds. The locomotive must burn additional fuel just to haul that extra mass across the rails. This is where rail's physical advantage over aviation transforms the economics of transport. Airlines also practice tankering, but the physical penalty of flight is severe. Because an airplane must generate aerodynamic lift to support every pound of onboard weight, carrying extra fuel increases drag and burns a significant portion of the reserve itself. For airlines, the price difference between airports must be substantial, often 30 to 40 cents per gallon, just to break even on the extra fuel burned during the flight. For a railroad, the steel wheel on steel rail minimizes this penalty. The incremental energy needed to roll 14,000 pounds of extra fuel over hundreds of miles is exceptionally small. A price spread of just 10 cents per gallon is often enough to make rail tankering profitable. By filling its 5,000-gallon tank to the brim in cheap jurisdictions, a locomotive carries its own discount across state lines. The practice shifts from a simple refueling routine to a precise exercise in financial arbitrage. A railroad schedule is a mathematical prediction, but the physical environment is unpredictable. When a dispatcher plans a run, they must treat the baseline fuel calculation as a best-case scenario, rather than a guarantee. On a complex network spanning thousands of miles, disruptions are a constant operational reality. Consider what happens when a route is suddenly blocked. A mechanical failure on a leading train or a track maintenance delay can halt a following train for 6, 10, or 12 hours. During these extended waits on passing sidings, the locomotives must remain active, continuously burning diesel to maintain air brake pressure in cabin systems. Weather introduces another layer of uncertainty. High winds, torrential rain, or heavy snow force trains to operate at reduced speeds, transforming a standard 8-hour run into a 20-hour struggle. On some routes, a severe blockage might force a dispatcher to detour a train entirely, adding hundreds of miles to the run. Under these conditions, the extra fuel in the tank is the only barrier keeping a multi-million-dollar train from becoming dead on the tracks. The consequences of actually running dry between depots are operationally catastrophic. If a locomotive exhausts its fuel on a main line, the entire train stalls, blocking all traffic behind it on a single-track corridor. Resolving this requires dispatching a rescue locomotive to haul the stalled train, or sending a mobile fueling truck over rough terrain to deliver diesel directly to the stranded unit. This process can paralyze a key division for an entire day, triggering a cascading wave of delays across the network. While public reports of locomotives running completely out of fuel are almost non-existent in federal safety records, this rarity proves the reserve works. This unused volume acts as a deliberate shield against operational chaos. The physical presence of thousands of gallons of unconsumed diesel at the end of a trip represents a calculated safety margin. The question is how railroads weigh the daily cost of carrying this extra mass against the financial risk of a single catastrophic line blockage. Evaluating this operational compromise requires a careful look at the numbers. While the physical advantages of steel rails minimize the penalty of carrying heavy loads, surplus fuel is not literally free to transport. Every gallon of diesel sitting in the tank adds mass, and moving mass requires energy. To understand the true cost of this strategy, we must separate the initial purchase price of the fuel from the ongoing operational cost of dragging it across the continent. For an individual locomotive on a single reconstructed assignment, this penalty can be calculated as a marginal burn rate. The additional mass of the unburned fuel increases the overall resistance of the train. To overcome this resistance, the engine must burn a small, measurable amount of extra diesel just to carry its own fuel cargo. This percentage remains tiny, but it translates into a real environmental burden. This carbon cost is an essential component of any honest transport accounting. Over a long journey, the incremental emissions from hauling thousands of pounds of unused diesel accumulate, adding to the railroad's footprint. Applying a single, universal figure to this additional fuel burn remains misleading. Without verifying the specific duty cycle, the throttle settings, and the exact route of a run, any flat estimate is unreliable. Operating conditions vary wildly between flat plains and steep mountain passes, meaning the exact energy penalty is unique to each trip. The physical cost is real. The decision to carry a massive fuel reserve is not a cost-free choice. It is a calculated business trade-off. The railroad accepts a continuous, minor energy penalty on every mile of track in exchange for the operational safety of a large reserve. The extra fuel in the tank is a physical weight that must be paid for in diesel and emissions, proving that even the most efficient transport system in the world cannot entirely escape the laws of physics. Stopping a 3,000-ton freight train to refuel is not like pulling a truck into a highway station. It is a major logistical disruption. A single refueling stop forces a train to idle for hours, racking up crew labor costs and extending terminal dwell times. It also exposes the train to routing delays and network congestion, since pulling off the main line means waiting for dispatchers to clear a path back onto a crowded corridor. By carrying extra fuel, a locomotive bypasses these intermediate stops entirely, preserving schedule flexibility and reducing overall transit times. This operational freedom is weighed against the physical cost of carrying the extra weight. In a typical price arbitrage scenario, hauling an extra 14,000 pounds of cheap Gulf Coast diesel burns a small, measurable amount of extra fuel. Yet when the price spread between regions is wide, the net savings after subtracting this carrying cost remain heavily positive. On the other side of the ledger sits the catastrophic risk of running dry. If a locomotive exhausts its tank away from a service depot, the consequences are immediate. The disabled train stalls blocking all traffic behind it on a single-track mainline. Resolving this requires dispatching a rescue locomotive or sending a mobile fuel truck over difficult terrain. The expected cost of a single-line blockage easily dwarfs the minor carrying penalty accumulated over thousands of runs. Some industry accounts place the cost of a single refueling stop between $2,000 and $5,000, while others claim railroads mandate a strict 15% reserve. Without access to highly proprietary railroad logs, however, these flat figures and fixed percentages remain unverified. In reality, there is no universal rule. The break-even point is a moving target, constantly reshaped by specific route geometry, locomotive assignments, and daily operating conditions. The 5,000-gallon integral tank represents a carefully calculated boundary for standard freight networks. But when a route is so remote and the cargo so heavy that even a full tank cannot support the run, railroads reach the physical limit of onboard storage. To bridge this gap, some operators rely on dedicated fuel tender cars, essentially massive tank cars coupled directly to the consist, functioning as a mobile extension of the fueling network. This strategy appears in extreme heavy-haul environments, such as the remote mining operations of the Pilbara region in Western Australia. Here, Fortescue Metals Group has historically run iron ore trains across an 1,100-kilometer route. To avoid intermediate refueling stops in the deep outback, a specialized fuel wagon loading gantry was constructed at Kanyeri Yard to load dedicated tenders. These cars carry an estimated 10,000 to 12,000 gallons of diesel, feeding fuel directly to the locomotives as they travel. Why not simply build a larger tank directly onto the locomotive? The constraint is axle weight. Modern road locomotives are already engineered to the absolute limit of allowable gross weight, often resting right at the safety threshold of 71,000 pounds per axle. Enlarging the integral tank would add thousands of pounds of concentrated mass, risking track damage and structural failure. A separate tender car solves this by distributing the fuel weight across its own wheels and axles. However, adding a tender car introduces a severe operational burden. It adds extra rolling equipment that must be inspected, coupled, and maintained. The fuel transfer systems require complex pumps and hoses that can leak or fail in harsh environments. Furthermore, hauling a heavy, non-revenue-producing tank car increases the overall draft load and rolling resistance of the train. Currently, this calculus is changing as operators transition towards zero-emission fleets. In the Pilbara, Fortescue is deploying battery electric units equipped with massive lithium-ion packs and regenerative braking, a shift that will eventually make diesel tenders obsolete. Yet during this transition, the fuel tender remains the definitive proof of the rail equation. It shows that when the distance exceeds the capacity of the frame, railroads will accept the substantial equipment, handling, and weight penalties of a tender car to avoid the ultimate operational disaster of running dry. The presence of unburned fuel in a locomotive's tank at the end of a run challenges how we define system performance. If we measure success strictly by the work required to complete a single, isolated movement, carrying thousands of pounds of unused diesel looks like an obvious failure. But a railroad is not a collection of independent trips. It is a continuous, interconnected network, where the end of one run is simply the starting point for the next. Network planning must prioritize subsequent possibilities over the completed movement. What looks like waste under one set of physical laws becomes an asset under another. Every mode of transport is bound by the physics of its medium and the constraints of its physical infrastructure. A system designed to operate in the air must treat mass as an active penalty. A system supported by steel rails can use that same mass to solve logistical challenges, converting weight into mechanical and economic advantages. Measuring a train's performance by the rules of flight is an analytical error. This mismatch suggests a broader pattern that extends far beyond transport systems. Across various industries, engineering designs and operational habits often appear redundant or inefficient when viewed in isolation. Yet these apparent flaws are frequently the exact mechanisms that keep the larger system stable. It forces us to reconsider how we evaluate design choices. What other practices in our engineered world look like waste, only because they are being judged by the rules of a completely different system? We've arrived at a fundamental truth of engineering. Efficiency is never absolute. As global transit transitions towards zero emissions, tomorrow's battery-powered fleets will face these same physical trade-offs. The next time you spot an apparently wasteful practice in the modern world, ask yourself, is it truly an error, or are you simply judging it by the wrong system's rules? Join the conversation in the comments below.